make a Lewis dot structure for formaldehyde. It's CH2O. So you recall that you need to follow these three steps: happy, remove, move. That's what we've talked about before, but now we're going to add an additional step. After we've completed a reasonable Lewis dot structure, we need to minimize the formal charge. So this problem is a nice demonstration of how we'll be minimizing formal charge. There are two possible skeletal structures for formaldehyde. One in which carbon is at the very center, and there's two hydrogens and an oxygen on it. And another possible skeletal structure is one in which we have a carbon and oxygen kind of in the center, hydrogens attached to each element. All right, so first let's draw the Lewis dot structure for this top skeletal structure. In our happy structure, we need to add enough electrons onto each element to make them have filled valence shells. Hydrogen, only needs 2 valence electrons. You can see that there are 2 around it in this bond. Carbon needs 8, but right now it has 4 electrons around it. It needs 4 more. So 1, 2, 3, 4. Same for oxygen. 1, 2, 3, 4, and then hydrogen only needs that 1 bond. This is our happy structure. How many electrons are needed for this happy structure? How many electrons are in this structure where all of our atoms have filled valence shells? Now we have 2, 4, 6, 8, 10, 12, 14 electrons needed for our happy structure. We need to remove electrons after we make our happy structure, and in order to know how many to remove, we need to find the difference between how many are needed for our happy structure and how many will be available to us. Now, the number available is going to come from the valence shells of each of our elements. Let's see, we have 1 carbon atom, and that brought 4 valence electrons. So there are 4 valence electrons brought from all the carbons. There was 1 oxygen. That brought 6 valence electrons. So 6 valence electrons come from all the oxygens. There were 2 hydrogens. Each one brought 1 valence electron. So there are a total of 2 valence electrons coming from all the hydrogens. 4 plus 6 plus 2. 12 valence electrons will be available to us. 12 valence electrons will be available to us. The number that we need to remove is the difference between needed and available. Needed minus available, 14 minus 12, is 2 electrons need to be removed from this structure. All right, so go ahead and erase 2 electrons. Now we need to move electrons so that each element has a filled valence shell. Now you can see that this hydrogen still has a filled valence shell. There are 2 valence electrons around it. This oxygen also has a filled valence shell. There are 2, 4, 6, 8 valence electrons around it. But this carbon does not have a filled valence shell. There are only 2, 4, 6. It needs 2 more electrons, so we need to move electrons towards it. Instead of just being shared, instead of just being on the oxygen, this pair of electrons can be shared by both the carbon and the oxygen. So go ahead and move those electrons in to form a bond, cross them out or erase them, and draw them in. All right, so now we have gotten all of our elements to have filled valence shells, and checking our work here, so we have filled valence shells, and we have the proper number of electrons. We know that we should only have 12 electrons on our structure, and there are now 2, 4, 6, 8, 10, 12 electrons. Excellent. This is how we would normally complete Lewis dot structures, but we're adding a new step, and that is to minimize formal charge. So I'll talk about formal charge in a moment, but first let us go ahead and draw the Lewis dot structure for this other skeletal structure as well. It's the following. And so we need to see that actually only one of these structures is viable because it has a minimized formal charge. So let's talk about what formal charge is, and then we'll get rid of the non-viable option. Okay, so formal charge is the electrical charge difference between the number of valence electrons of an isolated atom of that element and the number of valence electrons assigned to that atom in the Lewis dot structure. or really it's just kind of the number of electrons brought to the table from that atom of that element, which is just the number of valence electrons, which is the same as the group number for that element. And then subtract the number of electrons kind of belonging to it. Let me show you what that means. Yes, formal charge is equal to the number of valence electrons brought to the table from that element, dependent upon its group number, minus the number of electrons belonging to that atom. Or it's the number of valence electrons minus the number of electrons in the lone pairs on that atom, and also half of the electrons in the bond. So, as an example, okay, take a look at this carbon here. All right, so how many electrons are brought to the table for any carbon atom? You recall that the Lewis dot structure for carbon is the following. Carbon brings 4 valence electrons to the table because it's in group 4A on the periodic table. It brings 4 valence electrons, yet right now there are not 4 electrons kind of belonging to it. There are 2 electrons in the lone pairs on the carbon, and yes, there are 2, 4, 6 electrons around the carbon, but only half of them belong to the carbon, half of the electrons belong to the other elements, oxygen and hydrogen. So we have 2 electrons on the lone pair and 3 electrons in the bonds belonging to the carbon. There's a total of 2 plus 3, 5 electrons belonging to that carbon. You see that though carbon brought 4 valence electrons, it effectively now has 5 closer to it than to other elements, and therefore it has more electrons than it brought. It has now a -1 formal charge. Take the valence number of electrons, 4, subtract the number of electrons belonging to that element, and that's -1 for carbon. All right, so we can write a -1 sign on that carbon. What about oxygen? How many electrons are brought to the table from an oxygen? Oxygen is in group 6A. Its Lewis dot structure when it first comes in is the following. You see that it has 6 valence electrons. Oxygen brings 6 valence electrons, yet right now there are only 2 electrons in the lone pair on it, and there are 3 bonds. Each bond has 2 valence electrons in it, but only half of that number of electrons actually kind of belongs to the oxygen, is closer to the oxygen than to the other elements. And therefore, we have 2 plus half of 3, actually half of 6, or we have 2 plus 1, 2, 3. We have 5 electrons belonging to this oxygen, assigned to it. So 6 minus 5, it's a +1 charge on this oxygen. Yes, another way of viewing this is in the following depiction. You know that you can see that each of these X's or dots represents an electron, and I've given X's to this hydrogen and to this oxygen, and X's, we might say, are coming from these green elements, and these dots, these purple dots, are coming from the purple elements. We could see that carbon, it only brought 4 valence electrons to the table. These purple electrons, these are the ones that carbon brought. Yet, we can see that there are more electrons kind of within the sphere around this carbon. There are more electrons belonging to it or assigned to it than it brought. There are 1, 2, 3, 4, 5 electrons belonging to it. You can see that it originally had 6 protons and 6 electrons, but now that we have added this electron from the oxygen towards the carbon, we see that it now has 7 electrons around it. And so there's 1 more electron than proton around it. There is an overall -1 charge, having more negative electrons than positive protons. And then for oxygen, it's lost this green electron here. It's kind of assigned that now towards carbon. So it's lost an electron. It should have an overall positive charge. This is because oxygen originally brought 8 protons, but it now only has 7 belonging to it. There are 2, 4, 5 in the valence shell in principal energy level 2, and there are still 2 electrons in the 1s subshell on it as well. So 2 plus 5, there's 7 electrons kind of belonging to it. It has 8 protons, but 7 electrons. It has more positive than negative charge. There's an overall positive charge here. So we can see that there is a significant formal charge on this form of formaldehyde. But what about this form? Take a look at the hydrogens. They each brought 1 valence electron, and they each have 1 valence electron belonging to them. They have 0 overall formal charge. But what about the carbon here? Carbon brings 4 valence electrons. Right now it has 1, 2, 3, 4 electrons kind of belonging to it. No difference. 0 formal charge. Oxygen brought 6 valence electrons. Right now it has 2, 4, 5, 6 valence electrons belonging to it. 0 formal charge. There's 0 formal charge on this form. In fact, because there's no formal charge on this form of formaldehyde and a significant formal charge on this form of formaldehyde, we know that this will be the actual structure of formaldehyde. This is the more reasonable Lewis dot structure. You can see that the less formal charge, the better a Lewis dot structure is as a viable option. Now, if there must be formal charge, you want to have any negative formal charge on the more electronegative elements. We'll see this in the next video. Thanks for watching, guys.